You were told there were 9 planets, full stop, and then one day Pluto got kicked out like it never belonged. What changed? In this video, we're going to rip open that decision, follow the data that betrayed Pluto, and see why scientists now call it a dwarf planet, not the 9th world, and why that makes the solar system way more intense than your school textbook ever hinted. The version you were taught was very clean. 4 small rocky planets close to the Sun, 4 giant planets made mostly of gas and ice farther out, and then Pluto, small but still counted, orbiting in the deep dark. In that picture, Pluto sits around 5.9 billion kilometers from the Sun, about 3.7 billion miles, roughly 39 times farther out than Earth. 1 Pluto year is 248 Earth years. So if you were born today, Pluto would not finish even 1 orbit around the Sun in your lifetime. Every classroom poster showed it. Textbooks had a nice, evenly spaced diagram with Pluto at the far end. Quizzes asked you to name the 9 planets. Pluto was in cartoons, kids' shows, even jokes, so your brain tagged Pluto equals planet as a permanent fact. But here's the uncomfortable truth. That 9-planet layout was built on very incomplete information. When those posters were drawn, we basically had no detailed map of the region beyond Neptune. Our telescopes were weaker, our surveys were shallow, and the outer solar system was mostly guesswork. Pluto in the data was just a tiny moving dot that looked different from the background stars. We didn't really know what it was like, we just knew it was out there and orbiting the Sun, so the system worked like this. If something orbited the Sun and was not a comet with a long fuzzy tail, and we didn't know what else to call it, we slapped planet on it. That's not a careful, strict definition. That's a placeholder label that nobody bothered to tighten up for decades. Now here's where things start to crack. You were told Pluto is a planet alongside Earth, but it is absolutely not in the same size class. Pluto's diameter is about 2,376 kilometers, around 1,500 miles. Earth's is about 12,742 kilometers, close to 7,900 miles. Pluto is only about 2/3 as wide as our Moon, and the Moon itself is already much smaller than Earth. If you lined up Earth, the Moon and Pluto, Pluto would clearly look like the small one in the group. To feel that a bit more, think about travel time. If you drove a car at 100 kilometers per hour, about 60 miles per hour, and somehow you could drive in a straight line across Pluto with no obstacles, it would take you close to 24 hours to cross from one side to the other. One long day and you're done. To cross Earth at that speed, you'd be driving for several days. So calling Pluto a planet in the same sense as Earth hides a huge size difference behind one word. So why did early astronomers think Pluto might be almost as massive as Earth? Because at the start, all the key numbers about Pluto were weak guesses. We didn't know its true size, we didn't know how reflective its surface was, and we had no moons to track. All we saw was a faint moving point of light. From that, people tried to estimate how big and heavy it must be, and they were wrong. There was also a story in the background about a Planet X, a hypothetical large planet beyond Neptune that was supposed to explain tiny irregularities in the orbits of Uranus and Neptune. Some astronomers thought, those orbits are a bit off, so there must be a big object out there pulling on them. When Pluto was found, it was very tempting to say, great, that must be Planet X, so it has to be massive. The mass estimate wasn't based on direct measurement. It was based on a problem they were trying to solve and a convenient new object that showed up. The problem is, you cannot weigh a distant object accurately just from how bright it looks. A small, shiny, icy body can reflect a lot of sunlight and look deceptively bright. A large, dark body can look dim. If you assume Pluto is dark when it's actually bright, you'll think it must be bigger and heavier than it really is. That's exactly what happened. The situation only changes when you get something else to measure: a moon. Once you find a moon orbiting a body, you can track how long it takes to go around and how far away it is. From that motion, using basic gravity physics, you can calculate the total mass of the system. That's when fantasy ends and hard numbers start. When astronomers discovered Pluto's big moon, Charon, and measured its orbit, the results shocked people. Pluto's mass came out far lower than expected. It is around 1.3 times 10 to the power of 22 kilograms, which is only about 0.2% of Earth's mass. In plain terms, if Earth's mass is 100 units, Pluto's mass is about 0.2 units. Our moon, which you have never been asked to memorize as a planet, is more massive than Pluto. At that point, the mismatch became obvious. The label planet was riding on history and habit. The data were pointing somewhere else. Pluto was too small, too light, and too out of step with the other 8, but nobody rushed to change the textbooks overnight because there was emotion attached to the old list. People don't like giving up a simple story that they already learned. This is where the key idea kicks in. When someone asks, "Why isn't Pluto a planet anymore?" they're really asking, what is a planet exactly? Is a planet simply anything that orbits the sun and is round? If that's the rule, then you suddenly have to promote a lot of objects, including some large moons and many bodies in the outer solar system. Is a planet something that has to be big enough to control its orbit and push away other objects nearby? Or is a planet just whatever we agreed on when we were kids, and we don't want to update that agreement? Pluto sits right in the collision zone between those options. It is round, it has an atmosphere, it has weather, it has mountains and ice plains. In that sense, it feels like a small, real world, not just a random rock. But it is very small, very low in mass, and lives in a region that is full of similar icy bodies. In that larger context, it doesn't look like the leader of its orbit, it looks like one member of a crowd. So the main point of this first part is simple. Pluto didn't suddenly become less interesting. It never stopped being what it is. What changed was our measurement accuracy and our need for a clearer definition. The better we measured Pluto's size and mass, the worse it fit in the old word planet. The solar system did not change. Our map and our labels did, and that leads to the next step. If Pluto never really fit, then how did it get crowned as the 9th planet in the first place? What exactly happened during its discovery that set up this whole mess? And what did scientists misunderstand about that faint-moving dot at the edge of the solar system? You already know Pluto doesn't really fit with the other planets, so the next obvious question is, how did this tiny, icy world get promoted to planet in the first place? How does something that small and that misunderstood end up in every school book as the 9th planet, with basically nobody questioning it for decades? Back in 1930, a young astronomer named Clyde Tombaugh was working at Lowell Observatory in Arizona, and he was not actually looking for Pluto. He was hunting for something bigger, a hypothetical Planet X, a large world beyond Neptune that was supposed to explain tiny irregularities people thought they saw in the orbits of Uranus and Neptune. The idea was simple on paper. If those planets' paths weren't matching predictions exactly, maybe there was a hidden massive body beyond them, pulling with its gravity. To find it, Tombaugh used a very direct, very physical method. He took 2 photographs of the same patch of sky several days apart. Each plate was packed with stars. Then he put those 2 plates into a device called a blink comparator. It showed one plate, then the other, then back again, very quickly. The stars would stay put, but anything moving would jump back and forth. One of those tiny jumping dots was Pluto. Here's the twist that rewrites the whole story. Later, with better measurements and better models, astronomers realized those irregularities in Uranus and Neptune's orbits were basically just observational errors. The data on the positions weren't precise enough. There was no need for a massive Planet X to explain anything. Pluto didn't turn out to be the big hidden planet they were chasing. It just happened to be in the field of view. In other words, Pluto's discovery was real, but the original reason for looking for it was wrong. So now you have a faint moving dot, found during a search for a giant planet. What do you think the community is going to do with that? Call it a minor icy object and move on, or upgrade it to the new planet everyone wanted? That leads straight into the next problem: size. Pluto was extremely faint, around magnitude 15, which means you absolutely do not see it with your eyes. And even small backyard telescopes struggle. At that brightness level, astronomers in 1930 could not just look at the dot and say, Okay, it's this many kilometers across. They had to estimate. And this is where guesswork fills the gap. If you think Pluto is the object responsible for the supposed tug on Uranus and Neptune, then it cannot be a lightweight. It has to be massive. So that assumption leaks directly into the calculations. People treated Pluto as if it were heavy, maybe similar in mass to Earth, because that's what they needed to solve their Planet X problem. Once that thought is in the system, it spreads. Pluto enters the charts and textbooks as a planet with a roughly Earth-like mass, even though nobody had hard evidence for that number. You learned the story. You did not learn that the mass behind the story was basically a guess. So the situation for decades was, Pluto is called a planet, its mass is badly overestimated, and nobody has a good way to fix that. What breaks this setup is not opinion, it's new data. So what kind of data can actually force the issue? The answer is a moon. In 1978, astronomers discovered a large moon orbiting Pluto, later named Charon. This changed everything because once you have a moon, you have a clock and a ruler built into the system. You can measure how far Charon is from Pluto, on average about 19,600 kilometers, around 12,200 miles. You can measure how long it takes to go around once, about 6.4 days. If you know the distance between the two bodies and the time it takes to complete an orbit, you can use the standard gravity laws that tie together orbital period, distance, and total mass. You plug in those numbers, and out comes the combined mass of Pluto plus Charon. Subtract off Charon's share, and you get Pluto's mass. No guessing, no, maybe it's big because we want it to be big, just physics and timing. The result was clear and brutal. Pluto was nowhere near Earth's mass. It was not even close to the mass of our moon. Instead of being a big outer planet, it was a small icy body. The earlier idea of Pluto as a heavy, mysterious Planet X-style object evaporated. You're left with something more like an overgrown comet nucleus, or a typical icy body from the outer solar system, not a mini Earth hiding in the dark. So first, the Planet X motive collapses, then the mass estimate collapses. But there's another layer, how bright Pluto looks and what that brightness actually means. Here's the catch. Pluto's surface is quite bright in terms of reflectivity. Its albedo, the fraction of sunlight it reflects, is around 0.5 to 0.6. That means it reflects about half, or a bit more, of the sunlight that hits it. Fresh ice is very good at bouncing light back. Now, brightness in a telescope depends on both how big something is and how reflective it is. A small, highly reflective object can look about as bright as a larger but darker object at the same distance. Before we knew Pluto's real reflectivity, many people assumed it was darker, more like a typical dark rock or carbon-rich body. If you assume it's dark but you see it at a certain brightness, you end up thinking it must be bigger to reflect that much light. Later, once we understood its surface was covered with bright ices, the logic flips. A bright icy object doesn't need to be very large to appear as bright as it does. When you put in the correct reflectivity, the calculated size drops, so you can see how one wrong assumption stacks on top of another. First, you assume Pluto's the missing massive planet, so you push its mass up. Then you assume it has a dark surface, so you push its size up. Only when you get better data on its moon and its reflectivity do those stacked guesses collapse. And suddenly the ninth planet looks small, light, and out of its league. Now, add one more human factor: discovery bias. When Tombaugh found Pluto, it was a huge achievement. He spent countless hours scanning plates by eye, looking for that tiny jumping dot. This was not easy work. When the discovery was announced, newspapers around the world ran headlines like "New Planet Found." Nobody said "possible small icy body detected." The word planet was in the first big public story, and that word stuck. It stuck because it was exciting, because people wanted a new planet, and because at the time there wasn't much data to contradict it. Pluto's planet status was born in a data-poor era. Once a label like that locks into public consciousness, it's very hard to dislodge, even when new measurements show it was never quite right. So when Pluto was reclassified as dwarf planet in 2006, it wasn't an insult to Tombor. In a way, it was the opposite. It was using the data that his discovery made possible, plus decades of later work, to be more accurate about what Pluto actually is. Science didn't freeze the first guess in stone. It updated the label when the evidence demanded it. That leaves you with a rising tension. If Pluto was discovered because of a problem that turned out to be fake, sized by guesses that turned out to be wrong, and named a planet in the middle of newspaper hype, then what else about Pluto doesn't fit the clean story you were told? If the origin story is already this shaky, what happens when you look at Pluto's actual orbit and see how badly it breaks the normal planet pattern? You've seen that Pluto is small and light, but the real damage to its planet status comes from something you probably never thought about in school: its orbit. On a poster, every orbit just looks like a tidy ring around the Sun, but when you look at the actual numbers, Pluto's path is basically a giant red flag that says, "I did not form like a normal planet." Start with the basic layout. Most planets orbit in almost the same flat sheet of space called the ecliptic. That's just the plane of Earth's orbit, and the other planets sit only a few degrees above or below it. Mercury is tilted a bit, but still close. Jupiter, Saturn, Uranus, Neptune, all pretty flat. That's exactly what you expect if they all form together out of a thin rotating disk of gas and dust around the young Sun. Pluto ignores that pattern. Its orbit is tilted by about 17 degrees relative to this plane. 17 degrees doesn't sound huge until you picture the whole system as a flat disk. Pluto is not just slightly above the disk. It's noticeably out of the main level where the other big planets live. For something that's supposed to be a normal planet, this is your first sign that something is off. So you have to ask, what kind of history gives you an orbit tilted that much? A calm, smooth formation in the main disk, or a series of gravitational kicks and reshuffling in the outer solar system? The tilt is only part one. Part two is the shape of Pluto's orbit. The big planets have orbits that are very close to circular. They are slightly stretched, but the difference between closest and farthest distance from the Sun is not extreme. Pluto's orbit is much more stretched out. Its eccentricity is about 0.25, which means the distance from the Sun swings a lot over one orbit. At its closest point to the Sun, Pluto is about 30 astronomical units away. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers, or roughly 93 million miles. So 30 astronomical units is around 4.5 billion kilometers, about 2.8 billion miles. At its farthest, Pluto is about 49 astronomical units from the Sun, around 7.4 billion kilometers, or 4.6 billion miles. That is a huge change in distance for one object. There's another detail here that really breaks the simple 9-planet story you learned. For roughly 20 years out of Pluto's 248-year orbit, Pluto is actually closer to the Sun than Neptune. So there are stretches of time when the 9th planet is technically the 8th in terms of distance. Nobody told you on those school diagrams that sometimes Pluto jumps inside Neptune's average orbit. That's not how we expect a clean, layered system of planets to behave. So then you hit the obvious question. If Pluto's path crosses Neptune's distance from the Sun, why haven't they crashed into each other by now? Why has the solar system not had some huge catastrophic event involving Neptune and Pluto? This is where the orbit story stops being just weird and turns into something more precise. Pluto and Neptune are locked in what's called a 3:2 mean motion resonance. That just means that in the time Neptune completes 3 orbits around the Sun, Pluto completes exactly 2. Their orbital periods are linked in a stable ratio. Because of that ratio, the two bodies are never at the crossing point at the same time. When Pluto is at the part of its orbit where it comes inside Neptune's distance, Neptune is always somewhere else in its own orbit. The timing is such that close approaches are avoided over and over again. This isn't luck. It's a stable gravitational setup. This kind of resonance is not unique to Pluto. Many objects in the outer solar system share the same 3:2 resonance with Neptune. They are similar small icy bodies with similar orbital patterns. Astronomers even group them under a name, Plutinos. That alone tells you something important. Dynamically, Pluto doesn't stand alone the way Earth or Jupiter do. It is part of a whole family of small objects controlled by Neptune's gravity. So instead of seeing Pluto as a single oddball planet, orbital dynamics puts it into a category, one of many resonant Kyper Belt objects, shaped and controlled by Neptune's position and movement. That is a completely different role from major planet. Now you have to ask, how do you even get a setup like this? How do you end up with a big planet like Neptune and a swarm of smaller bodies, all arranged in neat resonances, many of them on tilted and stretched orbits? Computer simulations of the early solar system suggest a clear picture. The giant planets did not stay exactly where they formed. They migrated. In particular, Neptune seems to have moved outward from the Sun over time. As it did that, its gravity interacted with a huge population of icy bodies that were originally spread out in the outer disk. Some of those bodies were scattered inward or outward, some were ejected completely, some were trapped into resonances like the 3-2 pattern Pluto has. That trapping process naturally gives you orbits that are more tilted and more stretched compared to the inner planets, because these objects have been pushed around and locked into new paths by a moving giant planet. That story fits Pluto's orbit extremely well. A tilted orbit, a high eccentricity, a resonance with Neptune, and a position in a crowded region of small icy objects all line up with the idea that Pluto is one of many remnants of this early messy reshuffling. It looks less like a main architect of the solar system and more like a leftover piece that survived the chaos. This is why orbit matters so much for the planet definition. When the International Astronomical Union finally decided they needed a strict set of rules in 2006, they didn't just look at size and shape, they also looked at behaviour. One of the key points in their definition was that a planet has to clear its neighbourhood around its orbit. In simple terms, a planet must be gravitationally dominant in the region where it orbits. Pluto does not meet that standard. Its orbit is tilted far out of the main plane, it's strongly stretched, it crosses Neptune's distance, and it shares space with a large population of similar objects in the Kuiper Belt. It is not the dominant body in its orbital zone. Neptune is. The resonance locks that relationship in place. Neptune is the heavyweight. Pluto and the Plutinos are the small bodies that got captured and shaped by Neptune's gravity. So when you see Pluto's orbit drawn as a weird angled oval cutting inside Neptune's distance, you're not just looking at a line, you're looking at evidence. The orbit is like a record of Pluto's history, written in shape, tilt and timing. It tells you that Pluto is part of a belt population, controlled by a giant planet, not a standalone planet that carved out its own clear path. Once you accept that, the tension goes up another notch. If Pluto's orbit screams small captured body instead of dominant planet, then what about its physical size and gravity? Does Pluto have the strength to behave like a planet, or do the basic numbers of its mass and surface gravity push it even further away from the planet category? How can something smaller than a moon you don't even call a planet keep the title of planet for most of the 20th century? That's the next hard hit Pluto takes once you stop looking at posters and start looking at numbers. Pluto's radius is about 1,188 kilometers, roughly 738 miles. Earth's moon, the thing you casually call just the moon, has a radius of about 1,737 kilometers, roughly 1,079 miles. So the so-called ninth planet is only about 68% of the moon's diameter. In terms of volume, it's only around 1/5 of the moon's. If you line them up, Pluto would clearly be the runt. And remember, nobody calls the moon a planet under the official rules. That alone raises a simple question. If an object is smaller, less massive, and less tightly held together by gravity than a moon we already agree is not a planet, why did Pluto get the special treatment? If the moon doesn't qualify and it's bigger and heavier, it's pretty hard to defend a weaker object being promoted above it. This is where the emotional memory of 9 planets collides with a very basic size comparison that does not favour Pluto at all. But size is only one part. The next thing you have to look at is how strong Pluto's gravity actually is at the surface. Because if Pluto can't pull very hard, it can't shape its surroundings the way a major planet does. On Earth, you feel about 1 g, 1 unit of Earth gravity. That's about 9.8 meters per second squared. On Pluto, the surface gravity is only about 0.62 meters per second squared, around 0.06 g. So on Pluto, gravity is roughly 6% of what you feel on Earth. Put that into something you can feel. If you have a mass of 70 kilograms on Earth, about 154 pounds, the force you feel as weight drops to the equivalent of around 4 kilograms, roughly 9 pounds, on Pluto. You don't suddenly lose mass, but the pull downward is that much weaker. Your body would feel extremely light. Just walking would feel strange. A simple hop would send you far higher than you're used to. A trained Olympic high jumper who can clear around 2.4 meters, close to 8 feet, on Earth could in principle launch themselves tens of meters high on Pluto with the same leg power, because gravity is doing so much less to drag them back down. Day-to-day life, if you could stand the cold, would feel more like slow motion than normal walking. That very low gravity is not just a fun how high could I jump fact. It's a direct consequence of Pluto's small mass. It tells you Pluto doesn't have the gravitational muscle the 8 major planets do. It will struggle to hold on to a thick atmosphere. It will struggle to pull in and keep nearby objects. It will struggle to dominate a region of space full of other bodies. All of those things feed straight into the question, is this really a planet, or just a small world in a crowd? And there's another number that makes this painfully clear. Escape velocity. The speed you need to leave for good. For Earth, escape velocity at the surface is about 11.2 kilometers per second, roughly 25,000 miles per hour. That's the speed a spacecraft needs if it wants to break free of Earth's gravity and not fall back. That number is high because Earth is both relatively massive and relatively compact. Gravity has a strong grip. On Pluto, escape velocity is only about 1.2 kilometers per second, around 2,700 miles per hour. That's almost 10 times lower than Earth's. Now think about a modern rifle bullet. Typical bullet speeds are close to 1 kilometer per second, sometimes a bit more, sometimes a bit less depending on the weapon. On Pluto, that's in the same ballpark as the speed needed to leave the world entirely. So if you fired something off the surface of Pluto with the kind of velocities we casually reach with modern weapons or small rockets, you're already flirting with escape speeds. That tells you Pluto's gravity is barely hanging on to things at the surface. It also means the gas molecules in its upper atmosphere, especially the lighter ones, can leak away to space much more easily over long periods of time. A thin, fragile atmosphere fits a world like this. A thick, permanent planet-like atmosphere does not. Low escape velocity also matters for clearing the neighbourhood. A planet that can't fling away or capture smaller objects efficiently is not going to sweep out its orbit very well. It doesn't have the energy budget in its gravity to clean house the way Earth or Jupiter can. Pluto is in that weak gravity zone. It doesn't just fail the how heavy are you comparison, it fails the how hard can you kick comparison too. Now look at what Pluto is made of. Density is the key here. Water has a density of 1 gram per cubic centimetre. Rocks are typically around 3 grams per cubic centimetre or higher. Earth's average density is about 5.5 grams per cubic centimetre, because Earth packs a dense iron-nickel core and a lot of rock into a relatively small radius. Pluto sits at about 1.86 grams per cubic centimetre. That is much closer to mostly ice plus some rock than to solid rock and metal. The current understanding is that Pluto is roughly a 50-50 mix of rock and various ices, water ice, nitrogen ice, methane ice, and other frozen gases. That puts it in the same broad category as large Kyper Belt objects and even big comet nuclei, not in the category of terrestrial planets like Earth, Venus, or Mercury. So Pluto is not just small in size and mass, it's compositionally different from the inner rocky planets. It's an icy, mixed body from the outer solar system. It makes more sense to compare Pluto with other icy dwarfs and comets than with Earth or Mars. Its density fits better with frozen outer system leftover than core building block of a major planet. At this point, it's fair to ask, if size alone doesn't decide planethood, why does all of this matter so much? Mercury is also small, only about 4,880 kilometers across, around 3,030 miles. Why does Mercury get to stay a planet while Pluto doesn't? The answer is that size is a signal, not the whole verdict. Mercury is small, but it's very dense and relatively massive for its size. Its mass is about 3.3 times 10 to the power of 23 kilograms. It orbits close to the Sun in a region where it is the dominant object. There is no huge swarm of Mercury-sized bodies sharing its orbit. It has cleared its neighbourhood enough that, by the IAU's rules, it counts as a planet. Its gravity and position are enough to make it the clear boss of its orbital zone. Pluto, on the other hand, is small and light, and sits in a region that is full of other icy bodies. Its mass is only about 1.3 times 10 to the power of 22 kilograms, far below Mercury. It does not control its orbit the way Mercury does. It shares that space with many neighbours. So its small size and low density are not just random trivia. They are the first signs that dynamically and gravitationally, Pluto is in a different league. You can see the pattern forming. First, the orbit looks wrong for a classic planet. Then the size and gravity look too small for a classic planet. Then the composition matches outer belt objects more than inner rocky worlds. Each of these by itself is a warning. Together, they make it hard to keep Pluto in the same category as the 8 that really shape the solar system. So the next logical step is to ask, if Pluto doesn't belong with the main planets, where does it belong? What is its true neighbourhood? What population is it actually a member of? Once astronomers started answering that, Pluto stopped looking unique and started looking like just one of many similar icy worlds in a huge, crowded region beyond Neptune. If Pluto isn't really like the inner planets, then what is it actually a part of? And what else is out there with it that you were never told about? For a long time, Pluto looked like a lonely outpost, a single frozen world sitting at the edge of everything, and that isolation helped protect its planet status. If it's the only thing out there, it feels special by default. But that picture collapses as soon as we actually start looking hard beyond Neptune. For decades, telescopes just weren't good enough to systematically scan the deep outer solar system. So in the old data, you had Neptune and then Pluto, and then basically a blank. Starting in the 1990s, that blank started to fill in. Astronomers began running deep, wide surveys of the sky, taking long exposure images and carefully tracking faint, slow-moving dots night after night. And suddenly, Pluto was not alone anymore. They found dozens of icy bodies beyond Neptune, then hundreds. Now we know thousands. All of them are orbiting in a broad ring-shaped region that stretches roughly from about 30 astronomical units to about 50 astronomical units from the Sun. So from around 4.5 billion to about 7.5 billion kilometers out, roughly 2.8 to 4.7 billion miles. This whole region is called the Kyper Belt. In that context, Pluto is not the special edge object. It's simply one of the larger and closer members of this belt, and it just happened to be the first one that was bright enough and close enough for us to pick up with mid-20th century technology. If we had had modern surveys in 1930, Tombaugh wouldn't have found a single new planet. He would have found a belt. Once you accept that there is a whole Kyper Belt, the question changes from why is Pluto so weird to what kind of object is Pluto within this belt? Is it a giant among dwarfs, or just one more entry in a long list? When you look at the population of Kuiper Belt objects, or KBOs, you see a wide range of sizes. Some are just a few kilometers across, like oversized comets or large boulders. Others are over 1,000 kilometers across, so they start to become round under their own gravity and qualify as dwarf planets. Pluto sits near the upper end of that size range, but it is not alone there. Many KBOs share the same orbital personality features you already saw with Pluto. Higher inclinations, meaning they are tilted more out of the main planetary plane. Significant eccentricity, meaning their orbits are stretched, not close to perfect circles. And resonances with Neptune, like the 3-2 pattern Pluto has. When astronomers plot the orbits of these objects on graphs, inclination versus distance or eccentricity versus distance, Pluto does not stick out as some extreme exception. It sits comfortably in the same cloud of points as many other KBOs. In other words, if you make a histogram of sizes, Pluto is near the top but not alone. If you make a chart of orbital shapes and tilts, Pluto sits inside a continuous distribution. Statistically, it looks like the high end of a belt population, not like a separate category that deserves its own label. Calling it a planet while calling others KBOs becomes more of a historical habit than a description of real physical differences. That brings you to one of the key contrasts that kills the old 9-planet model: population versus dominance. In the inner solar system, each planet clearly dominates its own zone. Earth doesn't share its orbital neighbourhood with dozens of other Earth-sized objects. There are asteroids and near-Earth objects, but their total mass is tiny compared to Earth, and they do not come close to rivaling it. Out in the Kyper Belt, that picture breaks down. Pluto is not alone. It's one of many relatively large icy bodies. The belt is full of objects with similar compositions and related orbits. Pluto doesn't overwhelm the rest of the population, it just happens to be one of the bigger members. So if you're being honest with the statistics, Pluto looks like a member of a belt, not the emperor of its domain. That's exactly the difference the modern planet definition tries to capture. A planet is supposed to dominate its orbit, not just be one body in a swarm. Pluto, by the numbers, behaves like a swarm member, not a ruler. This isn't just theory, it's backed by deep observational work. Surveys like the Canada-France Ecliptic Plane Survey and others have mapped large chunks of the sky near the plane of the solar system down to objects only tens of kilometers wide. They carefully track these points of light over years to pin down their orbits. When you stack up all that data, you see structure. You don't just get one messy cloud. You see a classical Kyper Belt with objects on relatively low inclination, almost circular orbits. That's the dynamically cold population. Cold meaning low orbital excitation, not temperature. Then you see a more scattered, higher inclination, higher eccentricity population. That's the dynamically hot group. Objects that have been stirred up and pushed around more by Neptune and other interactions. Pluto fits into that hot resonant population, the part of the Kyper Belt that has been strongly shaped by the Neptune's migration and gravitational capture. That's not an opinion. It's what the orbital data show when you put Pluto on the same plots as everything else. Its orbit, its tilt, and its resonance line up with the hot Kyper Belt group, not with the calm, nearly circular orbits of the 8 major planets. Once you see the Kyper Belt as a real populated structure, you can't go back to the old picture where Pluto is a standalone 9th planet at the edge. Before the Kyper Belt, Pluto looked special simply because we didn't know about its neighbours. After the Kyper Belt, Pluto looks typical for that region. Icy, small compared to the major planets, and one of many. So Pluto's demotion is not about punishing Pluto or disrespecting its discovery. It's about cleaning up our categories after we finally realise that the outer solar system is far more crowded and layered than the school diagram showed. You don't keep calling one star the sun just because you found it first. You learn there are many stars and you make better labels, and this is where the tension jumps again. If Pluto is just one big member of a large belt, what happens when you start finding objects out there that are as big as Pluto, or even slightly more massive? If Pluto was kept as a planet, do you promote all of them too? Are you ready to jump from 9 planets to 20, 50 or more? That's exactly the crisis that hit when Eris, Haumea and Makemake showed up. Pluto suddenly wasn't even unique in size, and once that happened, astronomers had to choose: explode the planet list, or finally draw a sharper line that leaves Pluto on the dwarf side. How far can you stretch the word planet before it stops being useful at all? Pluto already looked shaky, but the real breaking point came when the universe basically said, "Here, have another one just like Pluto but a bit heavier." That object was Eris, and it turned Pluto from a sentimental favourite into a classification problem you could no longer dodge. In 2005, astronomers announced Eris, an object orbiting the Sun at about 68 astronomical units, so roughly 10 billion kilometers from the Sun, about 6.2 billion miles. Eris has a radius of around 1,163 kilometers, about 723 miles, very close to Pluto's radius of 1,188 kilometers. The crucial detail is that Eris is slightly more massive than Pluto, so now you have two icy bodies of almost the same size, both round, both far beyond Neptune, both with similar general properties, and one of them is heavier. Here's the corner that creates. If you keep calling Pluto a planet, there is no honest way to avoid calling Eris a planet too. You would instantly go from 9 planets to 10, and astronomers already knew there were more large Kyper Belt objects coming down the pipeline. So the question stopped being, is Pluto special, and turned into, are you ready for a solar system with maybe 20 or 30 planets once we finish counting? That is not a small change. It affects how you teach kids, how you write books, how you design diagrams, how you talk about the structure of the solar system. Eris didn't just show up as another frozen rock. It showed up as a test of whether the old definition of planet meant anything strict at all. And Eris wasn't alone for long. You then have to ask, what happens if Eris is not the only Pluto-like world that turns up? Not long after, 2 more big Kyper Belt objects were confirmed, Haumea and Makemake. Haumea is strange even by outer solar system standards. Along its longest axis, it's roughly 1,632 kilometers, a little over 1,000 miles, but it's not a nice sphere. It's stretched out like a squashed football because it spins extremely fast once every 4 hours. That rapid rotation bulges it out and gives it that elongated shape. It also has a couple of moons and a ring system. Makemake is more conventional in shape, roughly 1,434 kilometers in diameter, about 891 miles. It's bright, icy, and orbits in the same distance zone as Pluto and Haumea. So now, out past Neptune, you have Pluto, Eris, Haumea, Makemake, all in the same general size bracket. All round or very close to round under their own gravity, all icy, all on distant non-Earth-like orbits. Once those 4 are on the table, the illusion that Pluto is unique falls apart. Pluto is no longer the odd 9th planet. It's one member of a group of very similar objects. If you call Pluto a planet because of its size and shape, logic pushes you to promote Eris, Haumea and Makemake as planets too. And if you do that, where do you stop? That leads straight into the count problem. If your rule is anything that orbits the Sun and is round is a planet, then you have to go beyond Pluto and its immediate siblings. You have to look at the asteroid belt between Mars and Jupiter. There you find Ceres, roughly 940 kilometers in diameter, about 584 miles. Ceres is round. It has enough mass for its gravity to pull it into a roughly spherical shape. Under a round equals planet rule, Ceres is also a planet. And it doesn't stop at Ceres. Several other asteroids are close to round or would be round if they were slightly bigger. In the Kyper Belt, there are more objects that are near or above the size where roundness kicks in. As surveys get deeper, that list grows. Very quickly, you move from 9 planets to a system where you might be teaching 20, 30, or even more planets, and still leaving room for new additions whenever a new large KBO is discovered. From a pure data standpoint, that might be fine. The universe doesn't care if your list is long, but as a way to communicate the structure of the solar system, it becomes messy. You end up with a planet list that is so crowded with small bodies that the big architecture-defining world, like Earth, Jupiter and Neptune, no longer stand out in the terminology. The word planet stops highlighting the major players. So Eris didn't just add one object, it forced a choice. Either you accept a flood of new planets, or you clean up the definition so that planet means something about dominance and structure, not just shape. This is why people say Eris forced the vote. Before Eris, Pluto's status was uncomfortable, but you could ignore the problem out of nostalgia. After Eris, the inconsistency became obvious. You could not reasonably say Pluto is a planet, Eris is not, when Eris is slightly more massive and very similar in nature. The only honest options were, 1. keep Pluto as a planet and promote Eris, Haumea, Makemake, Ceres, and many future discoveries, accepting a large and growing planet list. 2. Redefine planet more strictly so Pluto, Eris, and the others are placed in a different, clearly labelled category. Eris didn't kill Pluto's planet status in some dramatic rivalry. It exposed that the category planet was never sharply defined in the first place. The science, the population of objects in the outer solar system, and the need for a consistent taxonomy all push toward a cleanup. The solution that astronomers settled on in 2006 was to introduce a new class, dwarf planets. The idea was simple but powerful. You separate two concepts that have been mixed together. First, you ask, is this object round under its own gravity? If yes, that tells you it's big enough to be internally organised, not just a loose pile of rubble, but a differentiated world with enough gravity to pull itself into a roughly spherical shape. Pluto, Eris, Haumea, Makemake, and Ceres all pass that test. Second, you ask, has this object cleared its neighbourhood? In other words, is it the dominant body in its orbital zone, or is it just one member of a crowd of similar-sized objects? The big 8 planets have cleared their neighbourhoods. Pluto, Eris, Haumea, Makemake, and Ceres have not. They live in belts or crowded regions. So the compromise classification is this. A planet orbits the Sun, is round, and has cleared its orbital neighbourhood. A dwarf planet orbits the Sun, is round, but has not cleared its neighbourhood. By that definition, Pluto is not a planet, it is a dwarf planet. Eris is a dwarf planet. Haumea, Makemake, and Ceres are dwarf planets. They are not failed planets. They are not less real. They are members of a recognised class of round, geologically interesting bodies that simply never became the gravitational bosses of their orbits. The new label doesn't downgrade their scientific value. It just stops pretending that an icy world in a belt and a giant like Jupiter belong under the same single word. But if you tighten the definition like that, you hit another problem. Now you need a formal global definition of planet that everyone can use, not just a list of examples. Who gets to decide that, and how do they justify the specific rules they choose? Who actually has the authority to say, Pluto, you're not a planet anymore? And how do you know they're not just changing the rules because it's convenient? If this was just a popularity contest, you could ignore it. But the Pluto decision sits inside a much longer pattern in astronomy, where the meaning of planet has already changed before, for the exact same kind of reason. Better data exposing a bigger population. Go back to the early 1800s. When Ceres was discovered in 1801, orbiting between Mars and Jupiter, it was labelled a planet. Then Pallas, Juno, and Vesta were found in the same general region. At that point, people thought, okay, we're just adding more planets, that's fine. For a while, the textbooks really did list them as planets, just like Mercury or Jupiter. But over time, telescopes improved, surveys went deeper, and astronomers realised that there weren't just 4 of these things. There were many, all packed into the same zone between Mars and Jupiter. The region we now call the Asteroid Belt turned out to be a whole belt of small rocky bodies, not a handful of special planets. Once that clicked, the labels changed. Ceres, Pallas, Juno, and Vesta were reclassified as asteroids, not because they disappeared or became less interesting, but because we discovered they were just the larger members of a big family. Sound familiar? First you find a few, you call them planets, then you discover the full population and you build a new category that makes more sense. So Pluto's story isn't some new unfair move, it fits that same historical pattern exactly. Ceres lost planet status when the asteroid belt came into focus. Pluto lost planet status when the Kyper Belt came into focus. In both cases, the universe didn't change. Our map of it did. Now jump to 2006. By this point, we know about the asteroid belt, the Kyper Belt, Pluto's small size, its weird orbit, and the fact that it has siblings like Eris, Haumea, and Makemake. The old "we all just know what a planet is" approach doesn't work anymore. You can't keep running on vibes when you're classifying entire populations of worlds. So the International Astronomical Union, the IAU, which is basically the global body that standardizes names and definitions in astronomy, had to do something that had never been done formally before. write down a definition of planet for our solar system. They settled on 3 tests, and they're very straightforward when you say them in normal language. First, the object has to orbit the Sun, not a star far away, not a planet, the Sun itself. Second, it has to be massive enough for its own gravity to pull it into a nearly round shape. That's what people mean by hydrostatic equilibrium. Past a certain size, gravity beats the material's strength and smooths it out. Third, it has to have cleared the neighbourhood around its orbit. That means it must be the dominant object in its orbital zone, having either swallowed, ejected, or controlled most of the other material near its path. Pluto passes the first test. It orbits the Sun, passes the second test, it's round. But it fails the third test. Its orbit is full of other Kyper Belt objects with similar sizes and overlapping paths. Pluto is not the clear boss of that region. This third test is the one that really cuts the list down. It's easy to get round if you're big enough and icy enough. It's much harder to become the gravitational heavyweight of your orbital zone. That last step is what separates the 8 major planets from dwarf planets, asteroids and belt objects. But how do you know if something has cleared its neighbourhood? That sounds vague unless you can put numbers to it. Astronomers do exactly that. They use parameters with names like the Stern-Levison lambda and the planetary discriminant, usually written as the Greek letter mu, to compare how massive a body is to the total mass of other stuff near its orbit. You don't need the exact formulas. The key idea is simple. If a planet's mass is huge compared to everything else in its orbital region, it scores a big number. If it's not much bigger than its neighbours, it scores a small number. Earth's discriminant value is enormous. The total mass of near-Earth asteroids and debris is tiny compared to Earth's roughly 5.97 times 10 to the power of 24 kilograms. Earth clearly dominates its orbit. Jupiter's dominance is even more extreme. It's more than 2 times the mass of all the other planets combined. Pluto, on the other hand, has a tiny discriminant value less than 1. That means the combined mass of other Kyper Belt objects in and around its orbital zone is larger than Pluto's own mass. Statistically and dynamically, Pluto is not in charge of its region. It's one member of a swarm. The numbers back up what you already saw from the orbital patterns. Under the IAU rules, that puts Pluto into the dwarf planet category. It orbits the Sun, it's round, but it hasn't cleared its neighbourhood. That label is not meant as an insult. It's a description. It tells you in one phrase that Pluto is a real world with enough gravity to shape itself, but not enough to dominate its surroundings like Earth or Neptune. From a scientific point of view, that's a refinement, not a demotion. Before 2006, Pluto was just a planet in a vague sense. After 2006, Pluto is a dwarf planet in the Kyper Belt, part of a specific group of objects with similar properties and similar formation histories. The new term actually carries more information, so why not just shrug and add more planets? Why not say, fine, Pluto, Eris, Haumea, Maker, Ceres, and many more, all planets, will live with a list of 50 names. Because then the word planet stops highlighting the major building blocks of the solar system's architecture. You end up mixing bodies that shape the layout of the system with bodies that are mostly shaped by it. A gas giant like Jupiter, that controls asteroid belts and redirects comets, gets thrown into the same bucket as an icy dwarf that can't even clear a narrow ring of space around itself. The IAU chose a definition that tracks dynamics and structure, not nostalgia. Planet becomes a word reserved for the objects that dominate their orbital zones and help define the overall shape of the system. Dwarf planet and other categories cover the smaller but still geophysically interesting bodies that live in belts and crowds. That decision doesn't tell you which worlds are worth studying. Pluto's still fascinating, Ceres is still fascinating, Eris is still fascinating. What it does is keep the vocabulary aligned with how the system actually works. But there's still one more pressure point in this whole argument. If Pluto is round, has an atmosphere, has mountains and glaciers, and clearly acts like a complex world on its own surface, are we really okay saying it's not a planet? Is being round not enough? That's where the idea of hydrostatic equilibrium comes in, and where another divide opens up between how planetary geologists think and how orbital dynamicists think. So if Pluto is round, has an atmosphere, has mountains and glaciers, how can you still say it's not a planet? That's the point where a lot of people push back, because round feels like a big, obvious threshold. It looks like a world, not just a rock. But in planetary science, being round is only step one. It tells you something important, but it doesn't settle the argument. The technical phrase here is hydrostatic equilibrium. All that means is this: the object is massive enough that its own gravity can pull the material into a nearly spherical shape. For icy bodies, that happens at a smaller size because ice is weaker than rock. Once an icy object is a few hundred kilometers in radius, gravity can usually smooth it out. For rocky bodies, you need to go a bit bigger before gravity wins over material strength. Pluto, with a radius of about 1,188 kilometers, roughly 738 miles, clears that threshold easily. It is well into the gravity makes me round zone. But that also means something else. Pluto is not special on this point. Several moons and dwarf planets meet this same condition. Hydrostatic equilibrium is not a VIP pass for a tiny club. It's a basic cutoff that a lot of objects cross once they're big enough. And that leads to a simple challenge. If roundness is enough to be a planet, what do you do with all the moons that beat Pluto at its own game? Look at Ganymede, a moon of Jupiter. Its radius is about 2,634 kilometers, around 1,637 miles. Titan, around Saturn, has a radius of about 2,575 kilometers, roughly 1,600 miles. Even our moon, which people casually treat as just the moon, is about 1,737 kilometers in radius, around 1,079 miles. All three are larger than Pluto in size. In volume and mass, they completely outclass it. These moons are not just bigger, they are complex. Ganymede likely has a subsurface ocean and a magnetic field. Titan has a thick nitrogen atmosphere, lakes of liquid methane and ethane, and weather. Our moon has volcanism in its past and a strongly cratered, geologically interesting surface. Under a simple, round and interesting rule, every one of these looks more planet-like than Pluto, but we don't call them planets. We call them moons or natural satellites, because they orbit planets rather than orbiting the Sun directly. That tells you something key about the current definition. Round and geologically active is not enough on its own. Orbit and dynamical role matter. Where you are and what you orbit is just as important as what you look like up close. So you have Pluto, smaller than several moons but round and active. If you promoted Pluto to full planet based only on its surface complexity, you'd have to ask why you're not doing the same for Titan, Ganymede and the Moon. If you aren't willing to promote those, then roundness and geology clearly cannot be the whole story. That said, Pluto absolutely is a real world, not a dead ice ball. New Horizons proved that in 2015. The spacecraft flew past Pluto and sent back detailed images and measurements. What it showed is a surface that's surprisingly active for such a small object so far from the Sun. You see vast nitrogen ice plains like Sputnik Planitia, where frozen nitrogen slowly flows like glaciers. You see mountains made of water ice rising 3 to 4 kilometers high, roughly 2 to 2.5 miles. You see signs of possible cryovolcanism, where instead of molten rock, slushy water or other ices may have erupted and resurfaced areas. There are regions that look geologically young, with few impact craters, meaning something has been reshaping the surface in the recent tens or hundreds of millions of years. That's impressive for a body only 2,376 kilometers wide, orbiting around 5.9 billion kilometers from the Sun, about 3.7 billion miles away. Pluto is not a frozen, inert pebble. It's a small, active world with internal heat sources and complicated surface processes. But again, if you use active geology as your main planet test, you run into trouble. Europa, a moon of Jupiter, has an ocean under an ice shell, and likely active tectonics or plumes. Enceladus, a tiny moon of Saturn, sprays water vapor and ice from its south pole, indicating a subsurface ocean and active geology. Titan has an atmosphere and surface liquids. None of those are called planets either. So interesting geology doesn't automatically unlock the planet label. Pluto's activity puts it in the same club as several large moons and a few other dwarf planets, not in a separate category above them. This is why hydrostatic equilibrium, being round, is treated as a necessary but not sufficient condition in the IAU definition. It's the first gate. If an object isn't round, it's clearly too small and too weakly bound to be considered a planet or a dwarf planet. It's just a small body, an asteroid, a comet, a typical minor object. Once you pass that gate, you know the object has enough gravity to differentiate internally, to have layers, to potentially be geologically active. Pluto is in that group, along with Ceres, Eris, Haumea, Makemake, and many large moons. That's the worlds category, if you like. Real surfaces, real geology, not just rubble piles. The second gate asks a different question. Has the object cleared its neighbourhood? Is it the main gravitational power in its orbital zone, or is it sharing that space with many similar bodies? That is where Pluto fails. It passes the shape test, fails the dominance test. The 8 major planets pass both. So the combination of round plus cleared orbit is what gives you a planet. Round without cleared orbit gives you a dwarf planet. Not round gives you small bodies, asteroids, comets, and so on. That structure might feel harsh for Pluto fans, but it's logically consistent. Scientists care about these cuts because they're not just arguing over labels on posters. Classifications affect how you design simulations, how you prioritize missions, and how you build theories. You don't model planet formation the same way you model belt population evolution. Those are different physical processes with different initial conditions. Pluto's roundness tells you it probably has an internal structure, maybe a rocky core, an icy mantle, possibly even a buried ocean layer. It tells you it has enough gravity for complex geology and an atmosphere, even if it's thin. That makes Pluto a valuable target for studying how small icy worlds work. But its failure to clear its orbit, its place in the Kyper Belt, tells you it didn't grow into a major planet. It stayed as part of a belt population, a leftover building block from the formation of the outer solar system. Studying Pluto is studying the ingredients, not the finished main course. Put simply, hydrostatic equilibrium tells you Pluto is a world. Orbital dominance tells you it is not a primary world. Both pieces matter. And that pushes you toward the next question. If clearing the neighbourhood is so important, what does that actually mean in terms of gravity and numbers? And how badly does Pluto lose that comparison against real planets like Jupiter? If roundness and geology aren't enough, then what really separates a planet from everything else? This is where the idea of clearing the neighbourhood becomes the real test, and this is exactly where Pluto collapses. It's not about feelings. It's about gravity and statistics. Under the IAU definition, a planet has to gravitationally dominate its orbit. That doesn't mean the orbit is perfectly empty. It means that over billions of years, the planet has either eaten, thrown out, or locked into stable patterns most of the other objects that started out in the same zone. It's the main gravitational player in that ring around the Sun. Jupiter is the clearest example of this. It's about 2.5 times the mass of all the other planets combined. Its escape velocity is roughly 60 kilometers per second, around 134,000 miles per hour. If you try to hang around near Jupiter with a small body, you either end up crashing into it, getting ripped apart, or being flung into a very different orbit. Jupiter reshapes its surroundings. It doesn't just live in its orbit, it actively controls a huge region of space. That's what gravitational bully means in this context. Not emotional bullying, but raw influence. The big planets bend the system around themselves. The small bodies, like most asteroids and Kyper Belt objects, are the ones getting pushed around. To make this less hand-wavy, astronomers use actual numbers. One of them is called the planetary discriminant, usually written with the Greek letter mu. It's defined as the ratio of a body's mass to the total mass of all the other stuff that shares its orbital zone. You don't need the formula, just what it measures. How much more massive the main body is compared to the clutter around it. For Earth, this number is huge, on the order of 1.7 million. That means Earth's mass is about 1.7 million times larger than the combined mass of everything else that can be considered to share its orbit, like near-Earth asteroids and small debris. Earth absolutely dominates. Even though there are a few rocks that cross or approach Earth's orbit, they are rounding errors in terms of mass. For Pluto, the discriminant is less than 1. That means the total mass of nearby Kyper Belt objects in similar orbits is larger than Pluto's own mass. Pluto is not even the main shareholder in its own orbital neighbourhood. It's one contributor among many. If this were a vote, Pluto would be outnumbered by the surrounding belt. That's the core problem. A planet in this dynamical sense is supposed to be the main body in its region. Pluto is statistically a member of a crowd. Calling it a planet is like calling someone the owner of a company when they hold less than 1% of the shares and dozens of others own more. The title doesn't match the numbers. So why does Pluto fail this test so badly? 2 reasons. It's light and it lives in the Kuiper Belt. Because Pluto's mass is only about 1.3 times 10 to the power of 22 kilograms, its gravity falls off quickly with distance and doesn't reach very far in terms of strong influence. It can hold its own moons, but beyond that, its ability to capture or eject other bodies is limited. It doesn't have the kind of deep gravitational well that lets Earth or Jupiter bully their environments. On top of that, the Kyper Belt is a crowded zone. There are many icy objects in and around Pluto's orbit, some only slightly smaller, some on very similar paths, some in the same resonance with Neptune. That means Pluto has never had a chance to sweep that whole region clean. It's sharing that zone with a large population that was never removed. Over the age of the solar system, about 4.5 billion years, a true planet in that region would either have grown much larger by accreting that material, or it would have flung a lot of it away through close gravitational interactions. Pluto did neither. It stayed small and the belt stayed full. Dynamically, that tells you Pluto is behaving like a belt object, not as the main sculptor of the region. Compare that to the inner planets. Earth does share its orbital region with some small bodies, near-Earth asteroids, a few co-orbitals, dust, but Earth's mass, about 5.97 times 10 to the power of 24 kilograms, completely overwhelms the mass of that debris. Those small objects are passengers in Earth's orbital zone, not rivals. Mars is similar. Its mass, about 6.4 times 10 to the power of 23 kilograms, is still enormous compared to the mass of nearby debris. Both planets have clearly carved themselves out as the dominant objects in their paths. The clearing is not perfect, no orbit is totally empty, but the dominance is overwhelming. If you took all the near-Earth asteroids and mashed them together, you wouldn't come close to Earth's mass. If you did the same with objects near Mars, you wouldn't come close to Mars's mass either. That's why, under the IAU rules, both are planets without question. Pluto simply does not come close to that level of dominance. In its neighbourhood, the belt is not a tiny leftover, it's the main thing. Pluto is one of its larger members, but not the controller of the region. That's why people say it hasn't cleared its neighbourhood. It hasn't even come close. And this is not about wanting orbits to look tidy on a diagram. Clearing the neighbourhood is really about formation history. In the standard picture of planet formation, small grains stick together into bigger and bigger bodies, then into kilometre-scale planetesimals, and eventually into a few massive cores. The ones that grow fast enough and large enough start sweeping up the remaining material in their zone. That process of growth and clearing is what makes a planet in the dynamical sense. If you look at an object and see that it has cleared its orbit, you're seeing the fingerprint of that dominant growth phase. It tells you this object reached the mass where it could remodel its surroundings. If you look at an object and see that it's round but has not cleared its orbit, you're probably looking at a survivor from the earlier stages, a planetesimal or dwarf planet that never took over its region. Pluto falls into that second group. It formed, it grew enough to become round, it developed internal structure and interesting geology, but it never took the final step into becoming the gravitational ruler of its orbit. It remained part of a belt population. So when Pluto was reclassified, the hidden message wasn't "you're not good enough." It was "your dynamical history is different." Pluto didn't grow into a main planet. It stayed as one of the outer system leftovers. That's scientifically valuable, because it means Pluto preserves clues about the early solar system that the big planets have long since erased. But if Pluto is part of a complex system with a big moon and several smaller satellites, doesn't that structure pull it back toward the planet side? If it looks like a miniature planetary system on its own, how do you still argue it's not a real planet? How do you deal with a not a planet that looks like it has its own mini planetary system? Pluto doesn't just orbit the Sun alone, it brings a surprisingly complex family with it. And that family, especially Charon, is a big part of why the debate around Pluto refuses to die. Start with Pluto and Charon together. Charon is not a tiny speck the way many moons are. It's about 1,212 kilometers across, roughly 753 miles, which is more than half of Pluto's diameter of 2,376 kilometers, about 1,477 miles. That size ratio is extreme. Most moons in the solar system are much smaller compared to their host planets. Charon orbits Pluto at a distance of around 19,600 kilometers, about 12,200 miles. That's not just a random number. It's close enough and the masses are similar enough that the center of mass of the system, the barycenter, actually lies outside Pluto's surface. In most planet-moon pairs, the barycenter is inside the larger body. The planet wobbles a bit, but the main motion is the moon going around the planet. With Pluto and Charon, both bodies orbit a point in space between them. That is why people call it a true binary system. You don't have a big planet with a tiny moon tagging along. You have two bodies of comparable mass locked together around a shared balance point. For a long time, textbooks just lumped Charon in as Pluto's moon, but dynamically that doesn't capture what's really going on. Their rotation and orbital timing make this even more unusual. Both Pluto and Charon are tidally locked to each other. Their rotation periods are the same as the time it takes Charon to complete one orbit. About 6.387 Earth days. That means Pluto spins once on its axis in 6.387 days, and Charon orbits once in exactly the same time. If you stood on Pluto, Charon would not rise and set. It would hang almost fixed in the sky over the same point on Pluto's surface, slowly turning but not drifting across the horizon. If you stood on the opposite side of Pluto, you would never see Charon at all. The same is true from Charon's side. Pluto would sit locked in one place in Charon's sky. This is not the usual planet with a fast-orbiting moon layout. It's more like two partners locked into a synchronized rotation, turning together around a shared center. That tight coupling is another sign you're dealing with a pair, not a dominant world and a tiny satellite. In terms of pure layout, Pluto-Charon looks more like a scaled-down double planet than a typical planet-moon system. Now add the rest of the family. Pluto has 4 much smaller moons: Styx, Nix, Kerberos, and Hydra. They orbit farther out, up to about 65,000 kilometers from Pluto, roughly 40,000 miles. These are irregular in shape, only tens of kilometers across, more like lumpy rocks than spheres. The best current models say the whole system probably came from a giant impact early in Pluto's history. A large body hit Pluto, debris was blasted out, and that debris eventually reassembled into Charon and the smaller moons. This is very similar to the leading model for how Earth's moon formed. A Mars-sized body hit the early Earth, debris formed a disk, the moon condensed from that disk. So when you look at Pluto and its moons, you are seeing familiar planetary processes: giant impacts, debris disks, moon formation, but operating at a smaller scale in the outer solar system. It behaves like a real-world system in miniature. Because of all this, some scientists argue that Pluto and Charon together should be called a binary planet system. Their argument is simple. You have 2 round bodies, both big enough to be geologically interesting, both orbiting a barycenter that lies outside either one. That looks like 2 planets orbiting a shared point, not a planet with a subordinate moon. The International Astronomical Union, though, does not currently recognise binary planet as an official category. Under their scheme, only Pluto gets to be the primary. Charon counts as a moon, even if it's unusually large. The IAU focuses on whether the pair as a whole meets the planet criteria, not on whether the barycenter is inside or outside the bigger body. This disagreement shows you something important. Pluto lives right on the edge of our classification systems. It is exactly the kind of object that reveals where the definitions start to strain. It has a binary-like setup with Charon, a small swarm of outer moons, and complex dynamics. It looks and acts more complicated than a typical minor body, but not quite like the 8 major planets either. So you might think, fine, if Pluto-Charon is really a binary planet, doesn't that upgrade Pluto again? Doesn't having this complex, almost planetary system around it push it back into the planet group? Here's the key point. Even if you granted the binary planet label, nothing about that fixes the main issue in the IAU definition. Binary or not, Pluto and Charon together still do not clear their neighbourhood. They still live inside the Kyper Belt, still share their orbital region with a large number of other icy bodies, still sit in a 3-to-2 resonance with Neptune, still lack gravitational dominance over their zone. The clearing the neighbourhood rule doesn't care whether the main object is single or double. It cares about total mass and total control. You could tie Pluto and Charon together, treat them as a combined system with a bit more mass, and you would still not get anywhere near the level of dominance that Earth or Neptune has in its orbit. So yes, Pluto-Charon is a beautiful, complex gravitational system. Yes, it looks planet-like in the sense that it has moons, tides, and a giant impact history. But under the current rules, complexity and binary structure are not what decide planethood. Orbital dominance does. On that test, the Pluto-Charon system still fails, and that sets up the next twist. Just when the debate over definitions was heating up, a spacecraft flew past Pluto and showed it to be even more active and sessile than most people expected. That didn't change its mass or its orbit, but it did raise a hard question. When a world this alive shows up, are you really comfortable telling people it's only a dwarf planet? You've heard the argument. Pluto's so detailed and alive, how can it not be a planet? And a lot of that reaction comes from one moment in time, New Horizons in 2015. Before that flyby, Pluto was basically a fuzzy blob in telescope images, a slightly brighter pixel moving against the stars. After that flyby, it became a place, with landscapes you can describe in plain language. So let's be clear on what New Horizons actually changed, and what it didn't touch at all. In July 2015, NASA's New Horizons spacecraft shot past Pluto at about 14 kilometers per second, roughly 31,000 miles per hour. At that speed, you do not get leisurely orbits and second chances. You get a single high-speed pass, a few hours in the sweet spot, and that's it. At closest approach, the spacecraft skimmed past at about 12,500 kilometers above Pluto's surface. That's only a bit more than one Pluto diameter away. In that tight window, its cameras and instruments turned Pluto from a tiny blur into sharp images with detail down to a few hundred meters per pixel. Cliffs, plains, mountains, hazes, all of it suddenly snapped into focus. Overnight, Pluto stopped being an abstract ice ball and became a world you could point at and say, "Look, right there, that's a glacier, that's a mountain." One feature in particular grabbed everyone's attention, the bright heart-shaped area on the surface. One lobe of that heart is Sputnik Planitia, a huge nitrogen ice basin roughly 1,000 kilometers across, so on the order of 600 miles. That is almost half of Pluto's diameter, a truly giant feature for a body that small. When scientists looked closely, they saw that the nitrogen ice wasn't just sitting there. It showed patterns, big polygon-shaped cells that look like the surface is slowly overturning from below. That kind of pattern is a sign of convection, where warmer material rises and cooler material sinks, like slow boiling, but in ice instead of water. Then they checked the number of impact craters on that plane. Fewer craters usually means a younger surface, because impacts haven't had as long to accumulate. The crater counts in parts of Sputnik Planitia suggest some areas are only about 10 to 100 million years old. Compare that to the age of the solar system, roughly 4.5 billion years. That is very young. It means Pluto is not just a frozen fossil, it's doing geology on relatively recent timescales. For something so small and far from the Sun, that surprised a lot of people. New Horizons also confirmed that Pluto has an atmosphere, even if it's incredibly thin. It's mostly nitrogen gas, like Earth's atmosphere, but at extremely low pressure. At the surface, the pressure is around 10 microbars, which is only about 100,000th of Earth's sea level pressure. That's thinner than anything you've experienced, even on the top of Mount Everest, but it's not zero. The spacecraft saw light passing through the atmosphere and scattering, revealing layered hazes reaching up to about 200 kilometers in altitude, around 120 miles. Those hazes come from sunlight breaking apart molecules and building more complex ones, a process called photochemistry. So you've got a tiny world with surface temperatures around minus 230 degrees Celsius, roughly minus 380 degrees Fahrenheit, sitting almost 6 billion kilometers from the Sun, about 3.7 billion miles out, and yet it still manages to sustain an atmosphere, hazes, ice flows, and active-looking terrain. That's a strong reminder that small and far does not automatically mean dead and boring. This is where people jump in and say, look how complex it is, it has to be a planet, right? And emotionally, that reaction makes sense. You see something that clearly behaves like a world, not a rock, and the word planet feels like the natural label. But here's the hard line. Complexity and beauty are not part of the IAU definition. The rules that strip Pluto of planet status never mentioned boring or simple as criteria. New Horizons didn't change Pluto's mass, didn't change its orbit, and it didn't remove the Kyper Belt from around it. It didn't make Pluto heavier, it didn't make its orbit less tilted or less stretched, and it didn't magically clear out the other icy bodies near its path. All the reasons Pluto fails the planet test under the current rules that survived that fly by untouched. What changed was our sense of how much interesting physics and geology can happen on a small dwarf planet. From the scientific side, the reaction was not, okay, Pluto looks cool, let's vote it back in. The reaction was, if one dwarf planet in the Kyper Belt is this active, how many more fascinating worlds are we ignoring out there? Pluto went from being treated as a single oddball X-planet to being the poster child for a whole class of objects. Round, icy, belt-dwelling worlds with their own internal heat, atmospheres, and complex surfaces. In a way, the demotion helped more than it hurt. Calling Pluto a dwarf planet placed it in the same box as Ceres, Eris, Haumea, Make, and other similar bodies. That makes it natural to ask for missions to dwarf planets and Kuiper Belt objects as a group, not just to Pluto by itself. You start to think in terms of populations, not exceptions. You stop asking, is Pluto special enough? And start asking, what does this entire class of small icy worlds look like? From the inner asteroid belt out to the distant Kuiper Belt. That shift matters when people are fighting over limited mission budgets and telescope time. If Pluto were just the 9th planet, you'd be tempted to focus on it alone and then move on. As a representative of a whole population, it becomes a reason to explore further. New Horizons didn't rescue Pluto's planet status. It boosted the scientific value of dwarf planets as a whole. So the honest summary is this. New Horizons made Pluto more alive in our minds, more detailed, more real, but not more planet under the official rules. It strengthened the idea that small icy bodies can be as geophysically interesting as the big planets. It also underlined the separation between two ways of thinking, one that cares about how a world looks and behaves on the surface, and one that cares about how that world sits and acts in its orbital environment. And that brings you right into the heart of the ongoing fight. Should planet be decided mostly by what's happening on the surface and inside the body, or mostly by how it shapes its orbit and its surroundings? Planetary geologists and orbital dynamicists do not always agree on that, and Pluto is stuck in the middle of that argument, acting like a test case for whose definition you care about more. So at this point you've got a problem that isn't just about Pluto anymore, it's about what you think the word planet is even supposed to do. Is it a label that cares about what a world is like on the inside and on the surface, or is it a label that cares about how that world behaves in its orbit, and how it shapes its surroundings. Different groups of scientists answer that differently, and Pluto is stuck right between them. On one side, you have a lot of planetary geologists. These are the people who stare at craters, volcanoes, ice flows, atmospheres, and internal structures. Their job is to treat worlds as physical places with weather, geology, chemistry, and maybe even subsurface oceans. From that angle, the orbit is almost background noise. What matters is this thing a world or just a rubble pile? So many of them argue for a geophysical definition of planet. In plain language, that definition says, if an object is big enough to be round under its own gravity, and it shows active or past geologic processes, it's a planet, no matter what it orbits or how crowded its neighbourhood is. Under that rule, Pluto is a planet. Ceres is a planet. Many large moons like Europa, Titan, Ganymede are planets too in a geophysical sense. They're all worlds with internal heat, complex surfaces, and interesting atmospheres or oceans. The Sun orbits, the orbital dominance, all of that is secondary. If you apply that geophysical definition consistently, the count explodes. You don't just have the 8 big planets plus Pluto, you end up with dozens of planets in our solar system. You'd include the classical 8, you'd bring in dwarf planets like Pluto, Eris, Haumea, Make, and Ceres, and then you'd add a long list of moons, the Galilean moons of Jupiter, Titan, possibly Enceladus, maybe even more as we gather data. The final list would easily run past 100 objects. From a scientific point of view, that's not a problem. It actually matches the richness of the solar system. There are that many world-sized bodies worth studying in detail, but it completely breaks the simple story you grew up with. You can't sell 9 planets to a classroom anymore. You'd be selling a catalogue longer than the list of countries most people can name. For public communication and basic teaching, that's a big shift. On the other side, you have orbital dynamicists. These are the people who focus on how objects move, how they interact gravitationally, how systems evolve over billions of years. For them, planet is not just a label for world, it's a role in the architecture. A planet is one of the big bodies that shapes the disk of material around the star, sculpts belts, controls resonances, and dominates its orbit. From that perspective, Earth and Jupiter are fundamentally different from Pluto and Ganymede, even if Pluto and Ganymede are geologically impressive. Earth and Jupiter help define the structure of the solar system. Pluto and Ganymede live inside structures defined by something else: belts, giant planets, and resonances. So dynamicists argue that if you blur those roles under one word, you lose an important distinction about who is driving the system and who is just along for the ride. The IAU definition you saw, orbit the Sun, be round, clear the neighbourhood, is basically a dynamicist-friendly compromise. It says, yes, roundness matters, but you don't stop there. You also insist on orbital dominance. That's why the 8 big ones get to keep planet, and objects like Pluto get pushed into dwarf planet. The label tracks dynamical power, not just surface complexity. Here's the twist that people don't always admit in the public fight. Both sides are right inside their own frameworks. If you care about geology and internal physics, it is perfectly reasonable to talk about geophysical planets, meaning any world that is round and active in some way. In that language, Pluto is a geophysical planet. Europa is a geophysical planet. They are worlds, not rubble. If you care about orbital structure and system architecture, it is perfectly reasonable to talk about dynamical planets, meaning bodies that dominate their orbits and clear their surroundings. In that language, Pluto is not a dynamical planet. It's a belt object. Jupiter, Earth, Saturn, Neptune, those are dynamical planets. Once you accept that, the picture gets clearer. Pluto is geophysically planet-like and dynamically belt-like. It sits at the intersection of 2 valid taxonomies. The IAU made a choice. They tied the official word planet to the dynamical definition, the one about clearing the neighbourhood. That's why officially, Pluto is not on the planet list, even though geologically it behaves like a small real world. So the argument you hear is not really about whether Pluto is interesting, Everyone agrees it is. The argument is about what you want the word planet to highlight. Do you want it to highlight internal complexity? Or do you want it to highlight orbital context and system architecture? And this is actually how science moves forward. It's not chaos. It's not people making things up by vote for fun. Reality turned out to be more complicated than the simple lists we started with. The outer solar system is full of icy worlds. The inner system has belts of small bodies. There are moons bigger than the smallest planets. Those facts force you to sharpen your language. Pluto landed right on that fault line. It forced astronomers, teachers, and the public to decide what they care about in a definition. It exposed the gap between the story you grew up with and the system we really live in. And once you change the definition, you don't just change one label, you have to redraw the entire map of the solar system. Not as 9 marbles on a poster, but as a structured system of populations, belts, and classes. So the next step is this. If Pluto's demotion is really part of a much bigger shift, how does that new map actually look? And why does removing Pluto from the planet list somehow make the solar system more interesting instead of less? How does taking one planet off the list somehow make the solar system feel bigger, not smaller? On the surface, Pluto's demotion looks like you lost something, but once you zoom out, you realise the opposite happened. The picture got more detailed, more layered, and honestly more serious. The old model you grew up with was very simple. 4 rocky planets on the inside, 4 giant planets on the outside, and Pluto tagged on at the edge as the oddball. That's it. No belts, no populations, no structure beyond small inside, big outside. It was easy to memorize, but it hid most of the real architecture. The new model replaces that flat list with a structure. You have terrestrial planets, the rocky ones, Mercury, Venus, Earth, Mars. You have gas giants, Jupiter and Saturn, mostly hydrogen and helium with deep atmospheres. You have ice giants, Uranus and Neptune, smaller, richer in water, ammonia, methane. You have dwarf planets, Pluto, Eris, Haumea, Makemake, Ceres and others. You have the asteroid belt between Mars and Jupiter. You have the Kyper Belt beyond Neptune. You have the scattered disk even farther out, with more eccentric and tilted orbits. And beyond that, a distant reservoir called the Oort cloud, probably holding trillions of icy bodies. Pluto's demotion didn't just knock it down a rung. It forced us to admit all those other components matter. You stop thinking of the solar system as 9 dots, and start thinking of it as a layered system of zones and populations. That's a more realistic picture, and it lines up with the physics of how systems form and evolve. A big shift here is learning to see populations instead of exceptions. For a long time, Pluto was treated as the weird one. It was the only small icy object on the planet list, so everything strange about it got framed as this planet is unusual. Once the Kyper Belt was recognised and populated with thousands of objects, Pluto stopped being the weird one and became a large member of a much bigger group. That's the same kind of changeover that happened with stars. You don't call every bright star the sun. You classify stars into red dwarfs, sun-like stars, giants, supergiants. You look at populations in the Hertzsprung-Russell diagram instead of treating our sun as the baseline for everything. With planets, the same logic applies. You don't call every round, icy object a planet. You group them. Major planets, dwarf planets, belt objects, moons. You see patterns in those groups. Pluto in that frame is not a misfit. It's a prototype. It shows you what a large Kyper Belt dwarf looks like up close. Eris, Haumea, Makemake and others are more data points in that same population. The labels shift from special oddball to member of a class, which is how science usually progresses. This new structure also lines up with modern formation models in a way the old 9-planet story never really did. Current theories like core accretion, combined with planet migration and scattering, predict something specific. A small number of big planets that form and grow, and a lot of leftover smaller bodies that never made it to full planet status. Some of those leftovers get trapped in belts, some get thrown into distant reservoirs, some become Trojans, some become comets. In these models, beyond the main planets, you naturally get belts of leftover planetesimals, the asteroid belt inside, the Kyper Belt outside, the scattered disk beyond that. Pluto is exactly the kind of object you expect to find there. A surviving building block, mostly ice and rock, preserved in the deep cold, never merged into a giant. So Pluto is not a failed planet that lost some competition. It's a successful relic. It gives you a sample of the stuff that built the outer planets. Demoting it from the planet list actually makes the vocabulary match the theory. Planets are the big ones that finish the growth race. Dwarf planets and belt objects are the ones that didn't, and that's valuable information, not a downgrade. You also have to think beyond our own system now. Astronomers have found thousands of exoplanets orbiting other stars. Some of those blur the line between planet and brown dwarf. They're so massive they might start fusing deuterium in their cores. Others blur the line between super-Earth and mini-Neptune. Are they rocky worlds with thick atmospheres? Or small gas planets with big envelopes? When you're trying to classify exoplanets, a vague nostalgia-based idea of planet is useless. You need clear categories. You need to separate things by mass ranges, compositions, and orbital behaviour. Having a solar system taxonomy that already distinguishes major planets, dwarf planets, belt objects, and moons gives you a training ground. You practice drawing lines here, where you have good data, so you can draw lines out there where you only see transits and radial velocity curves. In that sense, Pluto's demotion isn't just about our backyard. It's about building a language that scales to thousands of worlds around other stars. If you can't decide whether Pluto is a planet, you're going to struggle a lot when someone shows you a world that's 10 times Earth's mass, very close to its star with a puffy atmosphere. You need your definitions to be sharp or you lose track of what you're comparing. There's also a psychological twist. By dropping Pluto out of the Planet Club, we actually pushed it into a more important scientific role. New Horizons launched and flew past Pluto after the demotion. Future missions we're planning now to other dwarf planets and Kyper Belt objects are happening because we see them as a whole category of targets, not just one token misfit. Pluto basically became the gateway to the outer system. Once you accept that it's a dwarf planet in a belt, you start asking, okay, what do the others look like? How many kinds of icy dwarfs are there? How do they differ in composition, atmosphere, activity? Pluto's loss of status in the word planet increased its status as the first detailed example of a whole family. And there's a subtle gain here too. Kids who grow up with the new model aren't stuck on 9 planets. They learn about belts, dwarf planets, and reservoirs from the start. Their first mental picture of the solar system is closer to what the data actually show. It's more complicated, yes, but it's also more accurate and more flexible. It can absorb new discoveries without breaking. So in the end, Pluto's demotion did 2 things at once. It hurt nostalgia. The sentence you memorized in school stopped working, and it upgraded the science. The solar system went from a flat list to a structured system. Pluto went from being a mislabeled 9th planet to being the face of the outer icy worlds. But there's one last piece to nail down. If Pluto didn't change physically when we changed its label, then what did change? How do you separate the rock itself from the words we use for it? And what does that say about how science handles being wrong in public? On the day Pluto was demoted, nothing out in space actually changed. No explosion, no shove, no sudden shrink. On August 23, 2006, Pluto was still the same object it had been the day before, a ball of ice and rock about 2,376 kilometers wide, roughly 1,470 miles, with a mass of about 1.3 times 10 to the power of 22 kilograms. It was still taking 248 Earth years to go once around the Sun. The surface was still cold, the nitrogen ice was still there, the mountains of water ice were still there. The only thing that moved was a line in a definition, written by humans in a meeting room on Earth. That's the key point people often miss. The IAU vote did not reach out and downgrade a physical object. It updated the legend on the map you used to talk about that object. The rock stayed exactly where it was, doing exactly what it was already doing. Our description shifted to catch up with the data we'd collected over decades. From Pluto's point of view, nothing happened. That's because classification is a tool, not some law built into nature. Nature does not come with labels stamped on things. There is no planet sticker, no dwarf planet sticker, no asteroid tag built into the particles. We build those labels to organize our thoughts, to make models, to run calculations, to teach other people what we've learned. And sometimes, the old labels stop pulling their weight. You already live with this in everyday life. For length, you can use meters and kilometers or feet and miles. The object you're measuring doesn't change, only the unit system does. 1 meter and about 3.28 feet are describing the same length. But if you're doing physics or engineering, metric is cleaner. It fits the equations better. It keeps things consistent. The same idea applies here. Different planet definitions describe the same objects, but they emphasize different aspects. A geophysical definition emphasizes internal complexity and roundness. A dynamical definition emphasizes orbital dominance and system architecture. The IAU chose the dynamical route for the official word planet, because that's more coherent for how we model orbits, migration, and long-term evolution. Pluto did not become less real or less complex, and it just moved to a different box in the classification scheme. Where this hits you personally is in the gap between emotional attachment and scientific utility. Your memory of Pluto is tied to school, to that my very educated mother, style mnemonic, to posters with 9 circles and Pluto at the edge. You were told that list as if it were a fact, like gravity pulling you down at 1G. So when someone comes along and says, actually, it's 8 planets now, it feels like they broke a promise, that a feeling is valid. You invested effort into learning that old list. It's natural to push back when someone tells you it's wrong now, but from the science side, the question is colder and more practical. Does the new classification help us make better models, cleaner comparisons, sharper predictions? If the answer is yes, then over time the new scheme tends to win, even if it upsets a generation's nostalgia on the way. The metric versus imperial analogy helps here. Think about speed. A spacecraft can cruise at 15 kilometers per second. That's a precise metric number that drops directly into physics equations. If you translate it, that's around 33,600 miles per hour. You can also explain it as, at that speed, you could cross the continental United States in just a few minutes. The kilometers per second are what scientists plug into models. The miles and the comparison to crossing a country are what give your intuition something to grab. Planet versus dwarf planet works the same way. Dwarf planet is the precise category that encodes 2 things at once, round shape and failure to clear the orbit. It's like the kilometers per second. Planet, in sheer casual speech, is fuzzier. People use it for anything that feels like a world. That's more like the miles in the analogy. Scientists decided to formalize the precise version, while everyday language is still catching up, and probably always will lag a bit. So when you say in normal conversation, Pluto is a planet in my heart, nobody is going to drag you into a conference hall and argue. But when scientists build catalogues, decide mission targets, and write down criteria, they need a stricter system. That's where the official definition lives. The Pluto story is actually a good example of scientific humility, not arrogance. For most of the 20th century, astronomers used planet in a loose way. It was partly tradition, partly guesswork, partly lack of data. Then the data improved. We measured Pluto's mass properly. We mapped its orbit and its resonance with Neptune. We discovered the Kyper Belt and found other Pluto-sized bodies out there. At that point, the honest thing to say was, okay, our old use of this word was sloppy. We need to tighten it. That's not easy to do when millions of people have grown up with the older version. You know people will be annoyed. You know every headline will frame it as Pluto gets kicked out of the club. You know students will groan that their textbooks changed again. But you still do it because the job of science is to match the language to reality as closely as possible, not to protect childhood mnemonics. So Pluto becomes a case study in how science deals with its own mistakes and rough edges in public. First you over-promote something based on weak data, then you gather better data, realise the category is too broad, and split it into subcategories that track real physical differences. You accept the hit to your pride and your public image because the long-term gain is worth it. And that sets you up for the final question that everyone really wants answered clearly. After all this history, all these details about size, orbit, belts and definitions, what's the short version? When someone asks you, so why isn't Pluto a planet? How do you answer in a straight line, without dodging, without hand-waving, in a way that respects both the data and the story you grew up with? So after all this, if someone stops you and says, alright, just tell me straight, why isn't Pluto a planet? You need an answer that's tight, not a 20-minute lecture. Here's the clean version. Under the current rules, Pluto's almost a planet, but it fails the final test. It orbits the Sun, yes, it's round, yes, but it has not cleared its neighbourhood. That third part is where it loses the title. Pluto's small with a radius of about 1,188 kilometres, roughly 740 miles. Its mass is about 1.3 times 10 to the power of 22 kilograms, far below even Mercury, Eoli, and below our Moon. Its surface gravity is only about 0.62 meters per second squared, around 6% of Earth's 1G. On Pluto, a body that has a mass of 70 kilograms on Earth would feel the weight equivalent of roughly 4 kilograms, about 9 pounds. And it lives inside the Kyper Belt, a region packed with other icy bodies on similar orbits. Put that together and the picture is simple. Pluto doesn't dominate its orbit, it shares it. Dynamically, it fails the dominance test, and that's the cut that IAU decided matters for the word planet. You can boil the whole scientific case down to 3 big points. First, population context. Pluto is not a lone ruler at the edge of the solar system. It is one of many Kyper Belt objects. We've found thousands of icy bodies out there, and Pluto is just one of the larger members of that crowd. In that population, it looks like a top-tier belt object, not a special 9th planet. Second, orbital dynamics. Pluto's orbit is tilted by about 17 degrees, highly elongated, and locked into that 3:2 resonance with Neptune. It even spends part of its orbit closer to the Sun than Neptune does. That behaviour matches what we expect from scattered, resonant belt objects that got pushed around by migrating giant planets. It does not match the calm, nearly circular low-tilt orbits of the 8 main planets. Third, mass and dominance. Pluto's mass is too small, and the Kyper Belt around it is too full. When you compare Pluto's mass to the total mass of objects in similar orbits, Pluto loses. Quantities like the planetary discriminant make that obvious. Earth outweighs the debris near its orbit by a factor of millions. Pluto does not even outweigh its local population, as gravity can't sweep its lane clean. It can hold on to a few moons, yes, but it cannot reorganize the whole region the way a real planet does. So no matter how you slice it with those 3 angles, population, orbit and dominance, Pluto ends up in the large belt object category, not in the primary planet category. That doesn't mean Pluto is nothing. You should be very clear on what Pluto actually is. Pluto is a dwarf planet. That means it orbits the Sun, is round under its own gravity, but it has not cleared its orbital neighbourhood. It is also a Kyper Belt object, part of the big icy ring of bodies beyond Neptune. It's one half of a tight binary system with Charon, sharing a barycenter that lies outside Pluto itself, and it's a geophysically active world. It has nitrogen glaciers, water ice mountains, 3 to 4 kilometers high, 2 to 2.5 miles, a thin nitrogen atmosphere with hazes reaching up to about 200 kilometers, around 120 miles, and surface regions that look geologically young. So Pluto is not a demoted marble. It's a frozen laboratory sitting at the edge of the solar system. It's full of clues about ices, atmospheres, internal heat, and the leftovers from planet formation. It's more useful to think of it as the best studied example of outer icy dwarf than as a failed 9th planet. What does that actually mean for you? When you say Pluto isn't a planet, you're not saying Pluto is unimportant. You're not saying it's boring, you're saying the word planet is being used in a stricter way now, reserved for bodies that gravitationally dominate their orbital zones. Earth, Jupiter, Neptune, they control their neighbourhoods. Pluto doesn't. What Pluto dominates instead is your understanding of how science changes its mind. It's the example that shows you how new data can force a rewrite of a story you thought was settled. You can still, in casual talk, call Pluto a planet if you want, the same way people mix feet and meters, but in the scientific context, planet is now a more precise tool. Pluto sits on the other side of that line in a category that's just as real, just as physical, but more honest about its role in the system. So here's the hook to leave you with. Pluto didn't fall from grace, you just zoomed out. When you finally see the full outer solar system, the Kyper Belt, the dwarf planets, the scattered disk, insisting that Pluto must stay a planet is like insisting a city bus is a train, just because that's what someone told you when you were 6. The universe turned out to be bigger and more crowded than the poster on your classroom wall. The word planet had to shrink so the map could grow up, and Pluto, the X-planet, didn't get erased. It became your entry point into that bigger, messier, more interesting cosmos you were never shown in school. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.